It's a great pleasure to have with us Stefano Mantica from Eni, Italy. Stefano is a physicist who graduated in Italy at the University of Pavia, that is not far from Milan, in fact. And but since 1992, it works in what used to be Agip and now is Eni. That is the major, well, it started as an oil company and now is really an energy company covering many, many different aspects of energy production and distribution. In the company, focused on research and development and contributed to creating workflows and software tools for simulating multi-phase flows in porous media. And his approach involved utilizing mixed finite element and high-order finite volumes for accurate modeling. Over his career, Stefano studied several aspects of reservoir simulation, including fluid flow in fractured media, and employing techniques like history matching to align simulated data with the real-world observation, often employing inverse problem solutions. In recent years, Stefano shifted his attention toward geomechanical studies, emphasizing the importance of ensuring that production activities that production activity remains environmentally compatible. And in particular, the activity requires analyzing the mechanical behavior of subsurface formation under the influence of fluid extraction and injection, assessing risks such as subsidence and induced seismicity, and devising strategy to mitigate this effect while optimizing production processes. This is one of the webinar of the SAMGS group on computational geosciences. I remember that the group has an engaged site, however, is available only for people that are registered to SIAM, and also two websites where we have the general, let's say, information on the activity group. I remember that you're still in time to apply for SIAM, and in particular, remember that SIAM allows for free student memberships. In particular, students that are members of a SIAM student chapter can apply to SIAM for free, but also students that are part of universities or institutions that are academic members of SIAM can apply for free membership. And I also remind that every SIAM regular member in good standing can nominate up to 2 students for free membership. So if you don't have already nominated your students, you can still do it. This is the last but one seminar of this spring series. The last one will be given by Tord Arbogast, University of Texas of Austin, on the 9th of May, the same time as this one. I remember also that all webinars are registered and are available on the YouTube playlist. And now it's time to give the floor to Stefano. You can use the Q&A section to pose questions or raise your hand at the end of the talk. And we'll recall again the next time webinar by Tord Arbogast. So Stefano, the virtual floor is yours. I will stop sharing my screen.
Thank you very much, Luca. So I share my screen and go to the presentation. So as Luca said, my name is Stefano Mantica. I've been working at Eni since 1992. I've been doing several jobs in the field of reservoir simulation and geomechanical modeling. Today, I will talk about what we do in terms of geomechanical modeling for underground CO2 storage and geothermal projects. Of course, I will present works that have been done with many people in our company. This is the building where we work, but also in cooperation with important universities inside Italy and outside Italy. Here I have written the name of some of the people that have worked with us during those time, and which participated more or less directly to the outcomes that I will present during this talk. So starting with the outline, first of all, I will try to give you some motivation for geomechanics in the energy transition. Next, I will talk about the modeling approach, one-way versus two-way coupling of flow and geomechanics. Give some results on cap rock integrity and induced fractures, and focus the main of the talk on results on field example on fault stability, and give some conclusion and future perspective at the end. So the motivation. Of course, if you look at the global CO2 emissions from energy and industry during the years, starting from the beginning of the last century, there is, of course, a sharp increase in the emission of CO2 up to today, which takes us more or less at 38 gigaton of CO2 per year emitted in the atmosphere. Of course, there is the need to reduce those CO2 emissions to fight climate change. And if you look at the several scenarios that have been proposed for this goal, we see that there is, during the years that are to come, really a huge reduction in CO2 emission in the atmosphere. I will focus in the next slide on one of those scenarios, which is the net zero emission by 2050 scenario, but by the International Energy Agency. This scenario forecasts the complete reduction to zero of the emission in the atmosphere by 2050. So what are the actions that the International Energy Agency proposes? Well, many in several different fields, starting from the electricity and heat, which is the blue region, in industry and in the transport mainly. There are really a lot of actions, but I want you to focus on those two. The first one is the capture and storage of CO2 in 2035. The forecast is to capture 4 gigaton per year of CO2, which arrives at 7.6 gigaton per year CO2 in 2050. Another important action to reduce the emissions is the increment of geothermal power generation, which in the net zero emission scenario goes from around 100 terawatt hour of 2020 to more than 300 terawatt per hour in 2030. So geothermal power generation and capture and storage of CO2, of course, involve injecting fluids in the underground. A more close look to CCUS, which stands for Carbon Capture, Use and Storage. Carbon capture, use and storage is really one of the important processes for reducing greenhouse gases emission in the atmosphere. And it works by capturing and separating CO2 from gases emitted by large emitters like energy and cement production factories. The captured CO2 is separated and it is transported via pipeline, ships or trains or trucks. And at the end, it can be utilized for several industrial purposes like additive for cement production or biomass generation, or it is stored into geological formations like depleted reservoirs or saline aquifers. Up to now, mainly it is stored in saline aquifers, but there are really important motivations to also look at depleted reservoirs. But how much of this utilization and storage is divided into utilization and storage of CO2? In 2020, 75% of CO2, let's say, captured is used for several use, and only 25% is stored. But the forecast to 2050 is that the 93% of captured CO2 will need to be stored, and only 7% will be used for those purposes. So in 2050, around 7 gigaton per year of CO2 will need to be stored underground. And the International Energy Agency states clearly that reaching net zero will be virtually impossible without CCUS. So we need to study what is the effect of underground CO2 injection. So when we inject CO2 underground, or water or hydrogen or whatever fluid, of course there is a plume of this fluid that will propagate in the depleted reservoir or in the aquifer. This induces a pressure increase and a temperature decrease, because we are injecting a fluid which is colder than the rock underground. This can induce an uplift of the reservoir and the ground surface, which needs to be modeled. But also, if the injection is too much aggressive, there is also the possibility to induce fractures with CO2 migration into the cap rock or the overburden. And at that point, there is also the possibility of an interaction, a chemical interaction between the CO2 and the rock, either the reservoir rock or the cap rock or the overburden. And of course, there is a strong need to study what is the result of this interaction. There will be precipitation, there will be an increase of porosity due to dissolution. So the geochemical modeling is a key factor to properly study underground CO2 injection. Another effect due to the stress variation is the possibility of induced or triggered seismicity. And this is a key point that needs to be studied in order to guarantee the safety of a fluid CO2 or whatever injection project in the underground. Of course, every modeling study will be based on a 3D fluid flow model, which interacts with several CCS subsurface spatial studies: geochemistry, flow assurance, fault seal analysis, fault stability, cap rock integrity, or thermally induced fracture. So the continued interaction between the fluid flow model and all those different spatial studies is the key to guarantee the safety of a project. So let's go now to the modeling approach, one-way versus two-way coupling. So multi-phase poromechanics. Of course, what are at the base of a fluid flow model is what we know very well. It's the component mass conservation, which I've sketched here in the slide, together with the Darcy law. The primary unknowns are pressure and saturation of pressure of the phases and saturation of the different phases. So, of course, we see on the first line, it is the conservation of mass. The first term is the accumulation term. The second is the flow term. And the last term on the left-hand side is the source term. The flow equation is usually solved using a finite volume, and the solution variables are at the centroid of a grid block of a discretization grid. This is coupled to the mechanics, where a linear momentum balance is imposed. And in this case, the primary unknowns are the displacement. This equation is usually solved with finite elements, so the main unknowns, the primary unknowns, is on the nodes of the grid block. In the equation that I have written down, there is this important concept of effective stress, which was introduced by Terzaghi in 1992, which relates the total stress, the weight of, in some sense, the weight of the overburden to the pressure of the system. So we may see as the weight of the overburden is carried by the intergranular forces and by the pressure of the fluid, which is included into the pore space. Of course, the flow and the mechanics are linked in the sense that a change in pressure due to the production or injection of fluids into or from the reservoir induces a change in effective stress, which in turn induces a change in volume, and so a change in reservoir properties, permeability and porosity, which is the cause of a new change in pressure. So the two, flow and mechanics, are clearly linked together. So the approach, if we do not want to use a monolithic solution, because we have available really highly tailored software for the flow and for the mechanics, the approach that we have available are several. Let's start from the one-way coupling. Here on the right, I have sketched two time steps from time step Tn to Tn plus 1 and Tn plus 2. In one-way coupling, the flow is solved at time step Tn, and it proceeds independently of the mechanics at time step and the following time steps. After the flow solution is computed, then pressure is passed to the mechanical simulator at each time step without going back to the flow simulator. So this is good in some sense because it is fast. We do not need any communication apart from reading the pressure from the flow simulator, but we do not go back to the flow with the results of the mechanics. In two-way coupling, what we do is to run first the flow simulator, pass the pressure at the mechanics, and get back to the flow simulation with the stresses or with the displacement or whatever, and iterate up to convergence. Next, the next step of the flow simulators is performed, and new iterations are performed to pass pressure and stresses back and forth from flow and mechanics. And we advance in that way. So, of course, it is higher in accuracy with respect to one way, but it requires iteration and communication between the two solvers. Here is a recap of those one-way and two-way coupling with remarks, advantages and drawbacks. And in the last line of this table, I've also put what is called an explicit coupling. In explicit coupling, the passage of communication is the same as two-way, but only one iteration is performed at each coupling step. So this is in some way a good compromise between accuracy and runtime, but the change in pressure due to the change in stress are lagged by one coupling step, of course. Okay. So what is the strategy that we have adopted to solve this coupling? We have adopted a fixed stress coupling, which has been demonstrated to be unconditionally stable by Kim, Celepi, and Koanes. Here I have resketched the mass conservation equation in simplified form. And in this fixed stress strategy, there is a porosity correction in the flow simulator due to the results of the mechanical simulator, which is computed by fixing the stress from one sub-iteration to the other. We have implemented in some software tool this approach inside our company, where we have implemented a controller, which is a communication interface that exchanges information between the two simulators, the mechanical and the flow simulator, without reading and writing files. So the controller sends the stress to a fluid flow simulator. We use Echelon, which is a GPU-based compositional reservoir simulator. And the controller reads the pressure and sets the stresses to Echelon, while sending the pressure to a co-simulation engine by Simulia, which interacts with our main geomechanical simulator, which is Abacus. And this co-simulation engine allows for the exchange of pressure and stress back and forth. So we have implemented this without any file communication, but only with this controller. Okay, some validation and analysis of the coupling on synthetic problems. First of all, what is called the Dean's problem, it is based on a work by Dean et al. In 2006. It is modified, slightly modified from that. We have a single phase fluid, water, and a soft reservoir, really soft reservoir, 10 to the minus 3 bar to the minus 1 compressibility, which is embedded in a stiff non-pay region, 2 order of magnitude stiffer than the reservoir. The initial pressure is hydrostatic. We produce from one single well at constant rate. The boundary conditions are the usual: no displacement laterally perpendicular to the surfaces, and no vertical displaces at the bottom of the model. And for the reservoir, we have no flow boundary to the reservoir. So looking at the results, this is clearly a problem where the production induces pressure decrease, which induces a compaction that goes back to the pressure and increases the pressure locally. So we can see this effect at the beginning of the simulation. It can be seen, of course, only in the coupled simulations. This is what is called the Mandel-Cryer effect, which cannot be captured, of course, by the uncoupled solution. Also, the results in terms of subsidence are really very much different between the uncoupled and coupled solutions. And if we look at the pressure evolution for different coupling strength of the two problems, where coupling strength is defined as the ratio between the bulk stiffness of a fluid and the bulk stiffness of a solid skeleton, we see that for increasing coupling, it is natural that the results of uncoupled and coupled solution differ from one another increasingly. If we look at the number of coupling iteration in the bottom right part of the slide, by increasing the coupling, we need also to increase the number of iteration to convergence of the two simulators. So we can say that for tau, this coupling parameter, larger than 1, we have strongly coupled systems. For tau much smaller than 1, we have loosely coupled systems. But going from those results, it seems that we really need to run coupled simulations. But going to a real field case, we will see that the results are a little bit different. So this is a case where we have 25 years of CO2 injection after 30 years of wet gas production where the reservoir gets depleted. In this case, we have 7 producers and 60 CO2 injectors. We have discretized in the flow model with around 600,000 grid blocks, 130 layers and 9 components in the compositional simulation. We have coupled this flow simulation with a mechanical simulator where we have applied some kind of upscaling in order to reduce the number of degrees of freedom. Of course, the reservoir simulation is only limited to the reservoir itself, but in the mechanical simulator, also overburden, side burden, and underburden are included. So we have reached 1.5 million of degrees of freedom, also trying to limit the number by some kind of upscaling. If we look at the results, here I have plotted the gas production rate and the gas injection rate for the history match, which is let's say the period where production occurred, and for the forecast, which is the period of injection. And we can see that for the pressure evolution, the field pressure evolution, the simulation one-way, two-way explicit, and two-way iterative coupling solution are really superimposed one to each other. This is because if we compute the coupling strength, this coupling strength is really, really minimal. It is low. It is around 10 to the minus 3, 10 to the minus 2. So for this real case, and we can say that from our experience, for most real cases, especially for depleted gas reservoirs, the coupling is loose and one way is fine. Of course, one way is fine provided that we have consistency in the compressibility that are used in the reservoir and in the geomechanical modeling. Because in reservoir and in mechanics, we use some kind of compressibility. For example, if in the mechanics we use the Can-Clay elastoplastic model, which is defined by lambda and kappa, we can generate from that pore volume multipliers table to be used in the reservoir simulation. So pore volume multipliers table are the ratio between void ratio as a function of effective stress and void ratio at reference condition. And we can build really tables using kappa and lambda that can be digested by the flow simulator. And in that case, the flow and the mechanics are really compatible in terms of compressibility. This consistency use of compressibility is crucial for one-way coupling, but also for two-way coupling it is non-negligible, because the pressure which is computed by the flow simulator, even if will be corrected by the mechanics with the okay. So I was just saying that it is also important to have a consistency between compressibility when we use two-way coupling, because the pressure that is computed is the starting point for retardation, and it may be important to start from a good pressure field, which is computed with a good compressibility. Okay. So going to some results, caprock, now that we have was well-behaved coupled model, we can study the integrity of a caprock due to injection or production, building a geomechanical model coupled with fluid flow, where we can look at particular points in the caprock. Of course, if we need to study caprock integrity, we will need to have really fine mesh in the caprock and in the upper part of the reservoir. In this case, you can see that the plastic deformation, which may be an indication for failure, are concentrated on the flank of the field. And really monitoring in this case is key to follow unwanted caprock problems. In these cases, I've shown a 4D seismic monitoring in which the velocity of the sound waves in time may vary in the overburden, and may be the symptom of a problem there. Another important point locally around the injection wells is the cooling effect, because we inject a cold fluid in the underground, and this is as the effect of a reduction of the minimum stress, which can be which can let's say can be a condition for a fracture propagation more easily reached than with isothermal conditions. This is the reason why we also study near well bore with fully coupled porothermomechanical models, and look at the evolution of a temperature field and stress field, in particular minimum stress field around the injection point. Fault stabilities and real field examples of fault stability studies. Of course, fault stability is the event that leads to seismic events, because the seismic events are the immediate effects of a sudden slip on underground surfaces that are called faults. So the slip mechanism is simple in principle. We have an existing fault underground on which an effective normal stress and the shear stress are acting. The stability condition requires that the tangential stress is less than the frictional resistance to sliding of the fault, which is the friction, the coefficient of friction mu multiplied by the effective stress. So we can compute by modeling these Coulomb failure functions, which is simply the difference between the two terms, and verify if the Coulomb failure function is less than 0, and verify what is the evolution in time of the Coulomb failure function. So if we look at more circles, the Coulomb failure function is simply the distance of a point, of a stress of a fault from the failure line. And a fault will tend to slip if we have an increase of tectonic shear, delta tau, if we have a decrease in the coefficient of friction. In this case, this may be due to fault weakening, due to interaction of the CO2 with material of the fault gauge. Or we can have poroelastic unloading of a fault, or fluid injection that tends to move the Mohr circle to the left. And in particular, there is also another indicators of stability, which is the slip delta pressure, which is indicated by the blue arrow in the slide, which is the pressure which is needed for the fault to reach the failure line. Another stability indicator which is usually used, it is the slip tendency, which is the minimum friction coefficient that guarantees stability for a particular fault. Okay, so we have implemented in-house a workflow for study for stability. We start from, of course, data gathering. We have also a first screening of a risk, which is based on a risk matrix based on a work by Walters and Zobak in 2015. When we have implemented the probabilistic analysis of fault stability, which computes the slip delta pressure, and identifying critical faults with this approach can lead us to modeling with implicit or explicit approaches, which I will briefly show in a moment. So let's start from the analytical study. This is, I will go really very fast on this because starting from the 3D geometry, stress state of a fault and fluid injection data, several stress states can be studied and can be modeled in a probabilistic workflow where fault orientation friction can be distributions, and at the end we can get to distribution of probability of fault slip. In this particular case that I show here in the slide, for bottom hole injection pressure below 90 bar, there will be no fault slippage, also considering the uncertainty in the input parameters. Okay, the next step is the numerical modeling, which is the core of each fault stability study. We have implemented with this workflow together with Politecnico di Milano, with MOX people. Starting from the fluid flow model, we build a geomechanical model, in principle, without considering the fault surfaces. So without having the big problem of meshing the faults inside the geomechanical model. The fault stresses computed by the geomechanical model are a posteriori in post-processing projected on fault surfaces in order to compute the slip tendency indicators like Coulomb failure function or slip tendency. And this can be done at different times and compared with the friction coefficient. Let me just show some results for this real project that we have. This is composed by 3 fields, which are really high quality sandstone with porosity up to 25% and permeability up to Darcy. An high pay thickness, 150 meter, and good continuity, so injection is guaranteed. Those are 3 fields with more than 20 years of production history, in which extensive data have been gathered. And the process, the specificity of this project is that we plan to inject simultaneously in those 3 fields, with a maximum bottom hole pressure imposed to the project that is equal to the initial reservoir pressure. So the injection pressure will not go over the initial reservoir pressure before the start of the production. Okay, so the workflow is that we have identified the main faults that are in the worst shape, let's say, in terms of dimension, critical orientation with respect to the stress field in situ. We have identified those main faults with the analytical model, and then we have generated triangulated surfaces for the faults, and we have projected the stresses from the geomechanical model to those faults. And the last step, of course, is to compare the slip tendency with the friction coefficient. This is really important because different fault regions may exhibit different shale contents, and patches with higher shale content can be characterized by lower friction coefficients. So it is important to check that the slip does not increase with respect to pre-production and pre-injection values, and with respect to the friction coefficient that we think we have in situ. So here is the result for on the right, the plot on the right. I have plotted the slip tendency for each of the triangle of the surface of the fault. I have ordered starting from lower slip tendency to higher slip tendency. So this is the beginning of the production of the field at year 2000. The green one is after 20 years of production. We see that slip tendency is mostly decreased. So gas production has stabilized the fault, apart from some triangle, which slip tendency is increased. Of course, this is a porolastic effect. It's not impossible that during production slip tendency increases. But in any cases, I wanted to underline that we are always very much below 0.4, which is the initial slip tendency of the fault. After the end of the injection at year 2015, we have these red dots, and we see that the slip tendency more or less go back to the original values. The difference is really minimal with the initial start of the production of the field. The last step in our modeling approach, which is the most difficult, is represented by the explicit modeling of faults. In implicit modeling, we didn't include the faults themselves into the grading of the geomechanical model. In this case, the fault is represented in the grid, and it is also represented in terms of two faces which can slide depending on the stress of the field. This approach is really consuming in terms of CPU time, because the contacts need to be modeled. In the case that I will show in the following slide, we have modeled the contacts with Lagrange multipliers. So let me just show you a case where we have applied this explicit fault modeling to a field where we were injecting fluid in the underground. This was a project in collaboration with several universities. In particular, we have a regional scale model, which has been completed by John Shaw at the Harvard University for the structural modeling, and Ruben Coanes for the geomechanical modeling. And we have computed the CFF evolution on 22 principal faults. After that, we have extracted the most interesting region from this regional model, and we have performed inside ENI a local sector model with boundary conditions coming from the regional model, which is really highly detailed because we wanted to study a particular fault in this region. This fault is explicit, and we had the possibility to history match the seismic energy which has been released by microseismicity during previous years. And we have used this static friction law. I have also to say that another model starting from these sector scale models was performed by Jim Dietrich, where fluid pressure and stresses come from this sector model. He also has a detailed detailed fault geometry, and the history matched the number of microseismicity events. We in any history matched the energy, and Jim history matched the number of events. And the particular interesting thing is that he has been using his rate and state friction law, which entails the evolution of the friction coefficient depending on the stress and on the state of the fault. Okay, so the results. This field is really complex because it's really high faulted carbonate field. We can see on the right the history match of a regional flow model. It was a really complex task, but the results is pretty good. We can see for 4 wells. In green, there is the modeling results, and in the red dots are the measured data. As far as geomechanics, we have 5 stratigraphic surfaces implemented into the model. We have topography, the top seal, and the reservoir top, and 2 layers into the reservoir. And the normal stress field of a region is, and the stressing region of the stressing field of this region is normal faulting. Starting from this regional model, we have extracted boundary condition for the local sector model. We have calibrated a new model locally, fluid flow, and we also calibrated a new geomechanical model with really fine discretization of a fault surface. So if we go to this final slide of a history match, we can see on the top left that the pressures in the injection well is really well matched. On the bottom left, we have in black the historical registered seismic moment in time, and in blue the results of the seismic moment computed by the geomechanical simulator with sliding of the two fault surfaces. To get this result, we have calibrated the friction coefficient to a value of 0.5, around 0.5, which is really in the range of the results that we got from our lab testing, which have been performed together with La Sapienza University in Rome. On the top right of the slide, we have also computed the hypocenters of the seismic events. Here we have on the fault surface the total cumulative slip computed by the model, and you can see the point of the microseismicity on the slide itself. Okay, after 2014, there is practically no more activity on this fault. This is crucial, and this is important because with the modeling, it has been possible to define what are the safe conditions for the injection. We can run in forecast and see what happens by varying the injection rates, and for injection rates that we have, let's say, tested in this experiment, there are rates which are proven to be safe for this particular field in this particular region. So this is a slide to show you a recap for what is the modeling approach, advantages and drawbacks, but I think we skip this one. Some computation run times. On the left, number of degrees of freedom, number of time steps, and total CPU computational time on our high performance computing center with different number of CPUs. And we see that run times for the geomechanical model are not small. For our bigger model, we are in the range of 2.5 hours of CPU time. On the right, I have put also the percentage between for one of our simulation for the strawberry field, the percentage of CPU time for the geomechanical simulator and for the fluid flow simulator, and we see that 85% is taken by the geomechanical simulator. So conclusions. Carbon capture sequestration is a primary technology to contain CO2 emissions. Up to now, saline aquifers are the main storage site, but depleted reservoirs, in our view, are important alternative because we have really extensive geological characterization. We have a deep knowledge of reservoir dynamics. And since the hydrocarbon was there, proven the sealing capacity is proven. In this field, integrated numerical modeling studies are mandatory, and fluid flow and geomechanics are at the core. We've also seen that safe operation conditions can be defined using those kind of models. One of the future improvements that I'd like to mention is that we are testing surrogate models in order to reduce the solution time and fully integrate the uncertainty evaluation in the workflow. So I thank you for listening, and I'll try to answer if you have any questions.
Thank you, Stefano. If you want to ask questions, you can either write them on the question and answer, or also just simply open the microphone and talk, which probably is even simpler, as you prefer. Okay, so I will keep the question and answer section open so that if there are questions, I will just read them too. Okay. I start with a question, so just to break the ice. You showed in the model for fault reactivation that you are considering the case where the parameter mu is changing, right? How important is that, if you have any idea, and how and how can the CO2 interact with the material inside the fault to change that parameter?
Yeah, that's really important, because we are performing lab tests in order to see what is the interaction of CO2 with different core materials of a fault gauge, because CO2 can interact with minerals. It can vaporize the water locally and lead to salt precipitation. It can dissolve minerals from the rock, and so having an idea of what is the results of interaction, either in terms of petrophysical properties variation, permeability, porosity, or whatever, and also in terms of friction coefficient, is really crucial. We are planning and will perform in really not far from now lab experiments together with La Sapienza, where they have this apparatus that is useful to test friction coefficient under different temperature and fluid flow conditions. So we are planning to inject CO2 and see what is the result of this interaction. Of course, the interaction of CO2 with the fluid may take long. So we have experiments in our labs in order to see what is the different mineral composition from the interaction at long times.
Okay, there is a question in the question and answer section here. How do you typically obtain the fault geomechanical parameter for the simulation? If there are any characterization methods involved, or it's fully from model calibration?
Okay, this goes back a little bit to the previous question, but we mainly have a set of lab experiments. We have taken course, and we also have other, let's say, materials coming from the drilling that we can analyze, and we have a range of possible, let's say, let's talk about friction coefficient. We have a range in which the friction coefficient may lie, and we inside this range we can calibrate the friction coefficient with modeling. Up to now, what I have shown for the injection test case with explicit fault, we only have one friction coefficient for the whole fault surface. So that, of course, is a limit that can be overcome with, let's say, a much better characterization of the fault surface. But inside the uncertainties, I think that this is not a real limit, because we can face that uncertainty with multiple simulations with different friction coefficients, in order to be sure that the results lie in the range that we need to have.